Hello people, welcome back. The question is from GATE 2006 exam. It's for 2 marks. Before discussing this question, I like to discuss some basics for Booth's algorithm. Suppose you want to multiply two numbers. This is how you multiply two numbers. See, this is multiplicand, this one is multiplier. If the bit in multiplier is 1, copy multiplicand as it is. If this bit is 0, write zeros. Again this bit is 1, write the number as it is. Okay. In binary we have either a 0 or a 1. Multiplying with 1 means doing no change to this number. Multiplying with 0 means making all these bits zeros. Now, how can we mimic this process in computer? Step 1 is we need to generate the partial sums. These are called the partial products. I use the term partial sums. These are called partial products. We need to generate all of these partial products. Suppose first partial product is generated. Now we need to add it to the second partial product. But the thing is, this is not a normal addition. We need to have a 0 here, or you can say, more commonly people write a cross here. Okay. For this, we can shift this number to right. Okay. Performing a right shift, I'll get a 0 here. Then I can add this number. So start writing this number from the left hand side. So it is 000. Now whatever sum we get, the sum is 1110. Again perform a right shift like this and start writing the third partial product from here. Okay, now you add these two numbers, you will get 110001. Okay, so this is your answer. That means we can perform multiplications using very basic circuits that are shift registers and the adder. Okay, but the problem is this process won't work for signed numbers. See, what is the problem? While shifting this number, I automatically assumed a 0 is present here. Okay, I automatically assumed a 0 is present here as well as here. That is the problem. This is a negative number. I must assume there is a 1. Okay. And with this one and a few more modifications, you can derive the Booth's algorithm. So Booth's algorithm generates these partial products in a better way and then performs addition after shifting them one by one. Okay. So in Booth's algorithm, instead of keeping this multiplier as it is, what we do is we convert this multiplier into something called Booth's code. Okay, let's see the process. So I've taken an example. Suppose this is your multiplier. Okay, we need to analyze it bit by bit and then we are going to copy the multiplicand as it is or write zeros. If we have a 0, we'll copy zeros. And having zeros is beneficial because if you add zeros to some number, it is kind of doing nothing. Okay, so there are only two cases. Either you add zeros, that means do nothing, or add the multiplicand. But if you take this number as your multiplicand, that is the Booth's coded number, you have reduced the number of ones and you have increased the number of zeros. That means instead of taking this number as multiplicand, if you use this multiplicand, it's beneficial because we have less number of ones. Can we do so? Is replacing this number by this one mathematically correct? Yeah, it's correct. Both of the numbers are going to represent same value. See, what is this number? It is 9. So 5112 minus 4 minus 1 plus 2. So it's probably 509, you can check that. This one will also be equivalent. Okay, so both of these numbers represent same value. So Booth's algorithm uses the coded number as the new multiplier. Okay. Now, how do I know that this is the multiplier? For this, I've already told you such a table is used. We consider there's an imaginary 0 in beginning. 0 to 1 transition means -1. 1 to 0 transition means 1. Then again 0 to 1 transition means -1 and so on. Okay. No transition means you will output a 0. So we have no transition here. We are going to output a 0. How do I know that for no transition it must be 0, for 1 to 0 it must be 1 and so on? For this, please watch my theory lectures. I've explained it in a great detail. Actually, we are exploiting a property of these continuous ones. They can be written in powers of 2. Okay, so I'm not going to explain that here. It's topic for some other video. Rather, I've already made that video. Anyways, now using this is beneficial because we have decreased the number of ones. But sometimes if the multiplier is so that we are not able to decrease the number of ones, in such a multiplier, that is the worst case multiplier for Booth's algorithm. In such a case, you will not be able to decrease the number of ones. So we use modified Booth's algorithm. This modified Booth's algorithm is improvement to Booth's algorithm. Okay. In normal Booth's algorithm, 1-bit coding is used. This is for normal Booth's algorithm. This is for modified Booth's algorithm. See, in normal algorithm, why is this coding called 1-bit coding? Because for every bit of multiplier, you will have 1 bit in code. So 10-bit multiplier means a 10-bit code. But if you use 2-bit coding, a 10-bit multiplier will result only in 5-bit code. Okay, so we have kind of reduced the partial sums to half. Even if you have such an input for 10 bits, you will be generating only 5 partial sums. How many partial sums will be generated in normal Booth's algorithm? They will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, one partial sum for each bit. But why are we using this algorithm? Because for all of these zeros, you don't need any partial sum. Okay. So Booth's algorithm is beneficial. Moreover, it works for negative numbers also. Now let's discuss about 2-bit coding. Let's say we have this same number. This number only. I want to know its 2-bit coding. For this, there's a very easy process. Step 1 is you derive this 1-bit coding. And step 2 is you use this code to get 2-bit coding. Now for 2-bit coding, we are going to combine both of these bits into 1 bit. Similarly, both of these into next bit. Okay. Interpret this one as a binary number. What is this binary number? It is 2 power 1 into 1 plus 0. That means this is 2. Similarly, this binary number is 0. This binary number is also 0. What is this binary number? It is 2 power 1 into 0 minus 2 power 0 into minus 1. This one will become 0. This is minus 1. Okay. Sorry, we have a plus here. So this number will result into minus 1. And this will result into 2 minus 1, which is 1. Okay. So this is 2-bit coding. Now we can simply derive this code without even considering this step. From here, you can directly reach here. How can we do that? See, for this, keep on combining 3 bits. We consider 3 bits at a time to find this coding. Okay, you can read all of these points. So if you keep on combining 3 bits, and there must be an overlap of 1 bit. See this, we start from the imaginary 0 and we keep on making groups of 3. This is the first group. This is the second group. Okay, so just consider the first group. It is 0, 1, 0. First group is 0, 1, 0. 0 to 1 transition means minus 1 in this coding. Okay. and 1 to 0 transition means plus 1. So we got 1 minus 1, the first group. Now this represents 2. 2 times 1 means 2, and this represents 1. 1 times minus 1 means minus 1 only. So the code is 1. That means wherever you see this group 0, 1, 0, you are going to write 1. Okay. 0, 1, 0, where is it? 0, 1, 0, we are going to write 1. Okay. This is how we actually got that one. Now we can just skip this step. The first group is 0, 1, 0. Simply write a 1 for this. Second group is double 1, 0. Let's analyze this also. Double 1, 0. It is 0 to 1 transition means minus 1. 1 to 1 transition means no change. So this will become minus 1. That's how we got this minus 1. So you can skip this step and simply write 1, 1, 0 will lead you to minus 1. Okay. So you can get this entire table. So what are the benefits of using 2-bit coding? See, if we have 10 bits in the original multiplier, the coded number will be of 5 bits only. Okay. So we'll reduce the number of steps to half. 3 bits are combined to give 1 bit only. Actually, you can say 2 bits are combined because this bit will be counted twice. We have an overlap of 1 bit. So all in all, we will reduce the number of these partial products. Just pardon me if I use the word partial sum somewhere. Okay, I was confused between these two multiple times. I had to record this video twice. Anyways, we'll reduce the number of partial products to half. That is benefit of modified algorithm. Let's just have a look at these points also. It is called radix 4 booths algorithm. That's another name for this algorithm. And number of partial sums. Okay, this one is also products. Are reduced to half. We consider 3 bits at a time for finding the encoding. Yeah, already discussed. While making blocks of 3 bits, these blocks overlap by 1 bit. This one is also discussed. Length of multiplier must be even. Yeah, if you want to make a groups, length of multiplier must be even. Else in the last group, you will have only 2 bits or 1 bit. Okay, you can see that. But what if the length is odd? What are we going to do? Just repeat this last bit. Okay, sign bit extension. I hope you know that. So just increase the number of bits in the number to make a groups of 3. And shift is equal to 2 bit. In that normal method where we had 10 partial products, we were shifting by 1 bit. Okay, we had 1 cross at every step. Okay, in that paper pen method. Say you want to multiply 1 0 with 1 0. You will write 0 0 here and there is 1 cross. That is 1 shift. Now because we are reducing the steps to half, you will be having 2 crosses. Okay, so at every step there will be 2 shifts. And why do you think we have only 2, minus 1, 1, minus 2, etc.? Because multiplying with 2 is very easy. Multiplying with 2 also means a shift only. Okay. So multiplying with minus 1 means just taking complement of that number. Multiplying with 1 means doing nothing. The number is left as it is. Multiplying with 0 means outputting zeros. Okay. So now let us read the question and I'll just let you know its answer. So I think I have misplaced my mobile. Yeah, it's it. The question is, when a multiplicand y is multiplied by a multiplier x, so you can see x is a n-bit number, using bit pair recoding in Booth's algorithm, partial products are generated according to the following table. So just have a look at this table. We have already seen this table. We have actually seen how these partial products are derived. The partial products for row 5 and 8 are, row 5 is 100 and row 8 is 111. Okay. So they're asking what will be the partial product for 100. That means for this row and for the last row. Okay. You can see in 1-bit coding, when there is no change, 0 to 0, 1 to 1, we output a 0. Similarly, 0 to 0 to 0 and 1 to 1 to 1, we are going to output a 0. Okay. So multiplicand is multiplied with 0. In this case, they are saying the multiplicand is y and multiplier is x. Okay. So whenever such a pattern of 3 bits is seen, you are going to multiply the multiplicand, that is y, with 0. So this is 0 times y, which is 0 only. Okay. So row 8 will contain 0. And row 5. See, we have a transition from 0 to 0 and then 0 to 1. So let us also derive how did we get minus 2. The transition is from 0 to 0, then 0 to 1. 0 to 0 means no change, output a 0. 0 to 1 means block of ones is beginning, output minus 1. Okay, you can see it from this table. Now interpret this as a binary number. 2 power 1 into minus 1 is minus 2 minus 0. Okay, so you are going to get minus 2. That's the reason I've written minus 2 here. And now this will be the specific bit in the coded number. You are going to multiply this bit with multiplicand. Okay, I hope you remember all that stuff. When you have a 0, there's just outputting a 0. If you have 2, multiply the multiplicand with 2. So in this case, partial product will be minus 2 times y because multiplicand is y. Okay. So for row 5, it is minus 2y. So you can see your answer is option C, minus 2y and 0. Okay. Now let me just take one more minute to tell you how can this table be memorized. If you have memorized this table, this question is a cakewalk. It's like maximum 30 seconds and you have 2 marks. Okay. See, this last bit can be considered as the sign bit. Okay, last or first from whichever side you start. If this is sign bit, all of these numbers are positive. If this is sign bit, all of these numbers will be negative because 1 means negative. Now, no change means a 0, no change means a 0. It's just same as this table. Next thing is, in case of positive numbers, what is the biggest number? This number will have the value of positive 3. Okay, so for the biggest positive number, you just write 2. For rest of them, it's 1. Similarly, see, we need to know their 2's complement value. 2's complement value of this number will be minus 4. This is minus 3, minus 2, minus 1. So what is the smallest number? Smallest number is minus 4. Okay, in negatives you see the smallest number. For this, you are going to output minus 2. So for the biggest and smallest number, we are going to have 2 with the respective signs. Okay. You have also memorized this table now and I hope you understood all this stuff. So now if you guys want the shortcut and you haven't even memorized this table, then have a look. See, if at any time block of 3 bits is 0, 0, 1 or it is 1, 1, 1, that means 5th or 8th line, then what will be the partial product? So for that, first do 1-bit coding. That means the coding that is done in normal Booth's algorithm. So 1-bit coding for this will be 0 to 0, that means no change. So write a 0. 0 to 1 means block of 1s is starting. So write a minus 1. This is normal 1-bit coding that is generally done in Booth's algorithm. Now interpret it as a binary number to find 2-bit coding that is done in modified Booth's algorithm. If this is considered as binary number, weight of this will be 2 power 1 and weight of this is 2 power 0. So this number becomes minus 1 into 2 plus 0, which is minus 2. Okay. So in such a case, the output will be minus 2. That means the partial product will be minus 2 times the multiplicand. Multiplicand is given as y. So it is minus 2y. Similarly, here you can see 1 to 1 no change, that means 0. 1 to 1 again no change, that means here also it is 0. Okay. When we interpret this as a binary number, you are going to get 0 only. Okay. So in this case, we are going to output as 0. Now because output is 0, you can see the partial product will be 0 into multiplicand, which is 0 into y, which leads to 0 only. So your answer is minus 2 and 0. Okay.